So here's our diagram. We know that the radius is 6 inches, or by radius I mean diameter. The height is 6 inches. The base of the cylinder is 6 inches. And we also know that the coffee is draining. So dV dt is going to equal 10 inches cubed per minute. Anything else? So part A is how fast is the level of the pot rising when the height is 5 inches of the cylinder. Okay, so let's talk about the cylinder. The volume of the cylinder. What's the formula for the volume of a cylinder? Pi r squared h, right. And you can remember that because this pi r squared is the area of your base, and you slide it by your height, and that fills up the whole volume. Okay, and normally you take the derivative right away, but the height, or the radius, is a constant, isn't it? As the coffee fills your coffee pot, the radius always stays the same. It's not like sand where liquid kind of comes up in a cone, all right? And when you pour liquid, it stays level all the time. So that means R is what? What number specifically?
6.
6 is the diameter, so radius would be 3. Yeah. Oh yeah. So the R squared is 9. Yep. So the volume VC is equal to 9 pi h, which means dV dt is equal to 9 pi dh dt. And what do we know about dV dt? It's 10. So 10 equals 9 pi dh dt. So 10 over 9 pi inches per minute is equal to dh dt. Notice how the fact that it was 5 inches meant nothing to this problem. We didn't have to use this information at all. Okay, then part B. How fast is the level of the cone falling at that moment? So, the coffee in the cone is 5 inches deep. So this is of the cone, isn't it? Sorry. Still didn't affect this problem. Okay, so we have the volume of the cone. What's the formula for the volume of a cone? 1/3 of the volume of the cylinder. So 1/3 pi r squared h. Now here, r does not stay the same all the time. H does not stay the same all the time. But what we know is that this distance is 5. So I can set up a what? A ratio. Whenever you see cone problems, always look to set up a ratio. I could say 6 is to 6 as 5 is to what? What will this have to be? 5. That also will have to be 5. Actually, that's not true. It's not going to be 5. Because what was the radius of the big? 3. So it's really, so our ratio is 6 is to 3 as 5 is to our new radius. So that means 6r equals 15, or r equals 15, 6. Is that right? Yeah. At that moment? Yeah. Okay. Which is 5 over 2. Okay. You're right. But I realize we don't need that. In general, here's actually the general way we want to go about doing it. 6 is to 3 as your height is to your radius. This is better. Why is this better? Because now I can solve for r, and I can say r equals h over 2. And I can take, so this is my, r is my variable, and I can take h over 2 and plug it in for r. And it's going to make my derivative a lot easier, because it gets my derivative in terms of one variable. Why is that good? Because the 2 variables I have to use a product rule. If I can break it down to one variable, I don't have to use a product rule. So this equals 1/3 pi h over 2 squared h, which is pi over 12 h cubed. That's the volume of the cone. So, dv dt equals pi over 4 h squared times dh dt. What's the dv dt? It's not 10.
Negative 10?
It's negative 10 now, right? Because it's flowing out of the cone. So because you know, this is our derivative is a vector, and so it's got direction. So this is going to be negative 10 equals pi over 4. H was 5, so that's 25 dh dt. So that's going to be negative 8 over 5 pi, maybe? What were we looking for? How fast is the level of the cone falling? Is that the right answer, by the way? Answer your book, people.
Our solution to all these are really absurd ways of doing this problem.
Is that the right answer?
That's the right answer. I got when I did it.
Okay, sounds good. Let's stop that. Andrew,